Southern Observatory on Cerro Paranal in the Atacama Desert of northern Chile. The VLT consists of 4 individual telescopes, each with a primary mirror 8.2 meters across, which are generally used separately but can be used together to achieve very high angular resolution. The 4 separate optical telescopes are known as Antu, Quian, Milipal, and Upun, which are all words for astronomical objects in the Mapuche language. The telescopes form an array which is complemented by 4 movable auxiliary telescopes, UTs, of 1.8 meters aperture. The VLT operates at visible and infrared wavelengths. Each individual telescope can detect objects roughly 4 billion times fainter than can be detected with the naked eye, and when all the telescopes are combined, the facility can achieve an angular resolution of about 0.002 arcsecond. In single telescope mode of operation, angular resolution is about 0.05 arcsecond. The VLT is the most productive ground-based facility for astronomy, with only the Hubble Space Telescope generating more scientific papers among facilities operating at visible wavelengths. Among the pioneering observations carried out using the VLT are the first direct image of an exoplanet, the tracking of individual stars moving around the supermassive black hole at the center of the Milky Way, and observations of the afterglow of the furthest known gamma-ray burst. General information. The VLT consists of an arrangement of 4 large, 8.2 meter diameter, telescopes, called unit telescopes or UTs, with optical elements that can combine them into an astronomical interferometer, VLTI, which is used to resolve small objects. The interferometer also includes a set of 4 1.8 meter diameter movable telescopes dedicated to interferometric observations. The first of the UTs started operating in May 1998 and was offered to the astronomical community on April 1, 1999. The other telescopes became operational in 1999 and 2000, enabling multi-telescope VLT capability. 4 1.8 meter auxiliary telescopes, UTs, have been added to the VLTI to make it available when the UTs are being used for other projects. These UTs were installed and became operational between 2004 and 2007. The VLT's 8.2 meter telescopes were originally designed to operate in 3 modes. As a set of 4 independent telescopes, this is the primary mode of operation. As a single large coherent interferometric instrument, the VLT interferometer or VLTI, for extra resolution. This mode is occasionally used, only for observations of relatively bright sources with small angular extent. As a single large incoherent instrument, for extra light gathering capacity. The instrumentation required to obtain a combined incoherent focus was not built. In 2009, new instrumentation proposals were put forward to potentially make that observing mode available. Multiple telescopes are sometimes independently pointed at the same object, either to increase the total light gathering power or to provide simultaneous observations with complementary instruments. Unit telescopes. The UTs are equipped with a large set of instruments permitting observations to be performed from the near ultraviolet to the mid-infrared, that is a large fraction of the light wavelengths accessible from the surface of the Earth, with a full range of techniques including high-resolution spectroscopy, multi-object spectroscopy, imaging, and high-resolution imaging. In particular, the VLT has several adaptive optics systems, which correct for the effects of atmospheric turbulence, providing images almost as sharp as if the telescope were in space. In the near-infrared, the adaptive optics images of the VLT are up to 3 times sharper than those of the Hubble Space Telescope, and the spectroscopic resolution is many times better than Hubble. The VLTs are noted for their high level of observing efficiency and automation. The 8.2 meters diameter telescopes are housed in compact, thermally controlled buildings, which rotate synchronously with the telescopes. This design minimizes any adverse effects on the observing conditions, for instance from air turbulence in the telescope tube, which might otherwise occur due to variations in the temperature and wind flow. The principal role of the main VLT telescopes is to operate as 4 independent telescopes. The interferometry, combining light from multiple telescopes, is used about 20% of the time for very high resolution on bright objects, for example, on Betelgeuse. This mode allows astronomers to see details up to 25 times finer than with the individual telescopes. The light beams are combined in the VLTI using a complex system of mirrors in tunnels where the light paths must be kept equal within differences of less than 1/1000th of a millimeter over a light path of 100 meters. With this kind of precision, the VLTI can reconstruct images with an angular resolution of ms. Mapuche names for the unit telescopes. It had long been ESO's intention to provide real names to the 4 VLT unit telescopes, to replace the original technical designations of UT1 to UT4. In March 1999, at the time of the Paranal inauguration, 4 meaningful names of objects in the sky in the Mapuche language were chosen. This indigenous people lives mostly south of Santiago de Chile. An essay contest was arranged in this connection among schoolchildren of the Chilean II region, of which Antofagasta is the capital, to write about the implications of these names. It drew many entries dealing with the cultural heritage of ESO's host country. The winning essay was submitted by 17-year-old Jorsi Albanese Gostilla from Chuquicamata near the city of Calama. She received the prize, an amateur telescope, during the inauguration of the Paranal site. Unit telescopes 1 to 4 are since known as Antu, Sun, Quion, Moon, Mulipal, Southern Cross, and Upun, Evening Star, respectively. Originally there was some confusion as to whether Upun actually stands for the evening star Venus, because a Spanish Mapuche dictionary from the 1940s wrongly translated Upun as Sirius. Auxiliary telescopes. Although the 4 8.2-meter unit telescopes can be combined in the VLTI, their observation time is spent mostly on individual observations, and are used for interferometric observations for a limited number of nights every year. However, the 4 smaller 1.8-meter rods are available and dedicated to interferometry to allow the VLTI to operate every night. The top part of each rod is a round enclosure, made from 2 sets of 3 segments, which open and close. Its job is to protect the delicate 1.8-meter telescope from the desert conditions. The enclosure is supported by the boxy transporter section, which also contains electronics cabinets, liquid cooling systems, air conditioning units, power supplies, and more. During astronomical observations, the enclosure and transporter are mechanically isolated from the telescope, to ensure that no vibrations compromise the data collected. The transporter section runs on tracks, so the OTS can be moved to 30 different observing locations. As the VLTI acts rather like a single telescope as large as the group of telescopes combined, changing the positions of the OTS means that the VLTI can be adjusted according to the needs of the observing project. The reconfigurable nature of the VLTI is similar to that of the Very Large Array. Scientific results. Results from the VLT have led to the publication of an average of more than 1 peer-reviewed scientific paper per day. For instance, in 2017, over 600 refereed scientific papers were published based on VLT data. The telescope's scientific discoveries include direct imaging of Beta Pictoris b, the first extrasolar planet so imaged, tracking individual stars moving around the supermassive black hole at the center of the Milky Way, and observing the afterglow of the furthest known gamma-ray burst. In 2018, the VLT helped to perform the first successful test of Einstein's general relativity on the motion of a star passing through the extreme gravitational field near the supermassive black hole, that is the gravitational redshift. In fact, the observation has been conducted for over 26 years with the Symphony and Naco adaptive optics instruments in the VLT, while the new approach in 2018 also used the beam combiner instrument Gravity. The Galactic Center team at the Max Planck Institute for Extraterrestrial Physics, MPE, had used the observation revealed the effects for the first time. Other discoveries with VLT signature include the detection of carbon monoxide molecules in a galaxy located almost 11 billion light-years away for the first time, a feat that had remained elusive for 25 years. This has allowed astronomers to obtain the most precise measurement of the cosmic temperature at such a remote epoch. Another important study was that of the violent flares from the supermassive black hole at the center of the Milky Way. The VLT and apex teamed up to reveal material being stretched out as it orbits in the intense gravity close to the central black hole. Using the VLT, astronomers have also estimated the age of extremely old stars in the NGC 6397 cluster. Based on stellar evolution models, 2 stars were found to be 13.4 plus minus 0.8 billion years old, that is, they are from the earliest era of star formation in the